Some more conservation of energy. I like example one. I like example one. Example one is a nice question. The slingshot, it says, is pulled with an average force of 70 newtons for a distance of 90 centimeters. Oh, already, what's the first thing I would do with that 90? Yeah, 0.9. Nice try, Duick. How much potential energy is stored in the slingshot? The reason I wanted to talk about this is for a slingshot or a bow and arrow or any kind of device where you're stretching something like a catapult, the potential energy is not MGH. Every year I give this on a quiz or a test, and I have some kid that goes to part B, takes that mass, treats this like a height because it's in meters. That's not a height, and it's not gravity. This is not MGH. So here's my question. How the heck can I figure out how much potential energy is stored? Yeah. Okay. And energy is the ability to do work. So the other way we've done work is force times distance. They gave me a force, it's 70. They gave me a distance, 0.9. They are in the same direction. I checked. The force, by the way, for a slingshot isn't constant. It is changed. That's why I said average force. That lets me get away with this question. And I end up with, is it 63 joules? Someone want to double check me? Should be 63 joules of energy, of work done, of energy stored. So that's the potential energy, not as MGH, but as work. There's a 35-gram mass in the slingshot, in the pouch. How fast will it leave the slingshot? Okay. Here, again, this is conservation of energy, but I'm not going to do a full equation. I'm just going to argue all of the stored energy at the beginning is going to turn into kinetic energy, because once I let this go, all that energy that I stored is going to go out. The slingshot's going to hang limp and loose. This would be the same if I gave you a bow and arrow question as well. Slingshots, bow and arrow, same physics. So I think I can safely say 63 equals a half mv squared. Times by 2, divide by m. Here the mass does not cancel. If I tried launching a bowling ball with a slingshot, not going to go very fast. V is going to be 2 times 63 divided by 35. Nice try, Duick. Grams. 0.035 kilograms. And don't forget the square root. This will work out evenly, I think. 60. Does that seem right? I don't know how many of you have shot a slingshot. When I was a boy growing up, we went camping, and whenever I went camping with my dad, on the first day he would take his sons into the woods and he would carve each of us a slingshot. And so I have spent many, many hours firing a toy slingshot. 60 meters per second, that's about half of the length of a football field in a second. That's fast, but not crazy fast. That seems ballpark right to me. Tarzan weighs 82 kilograms and can run at 8 meters per second. He runs along the ground and grabs a vine, swinging into the air. What maximum height does he reach? I'm going to dulp. So here's Tarzan running. And here's the vine. And I guess when he grabs it, he's going to swing up into the air. Braden, is there going to be a change in height? Change in speed? Is there a yucky curvy path? Conservation of energy. I'm going to solve this by going KE initial plus PE initial equals KE final plus PE final. Braden, are any of these zeros? Yeah, we're going to, this is a bit of a wonkiness. Let's assume this is the center of mass. We'll put it the same height as here. Let's put the ground right there. Let's let PEI be 0. It'll all work out as long as I have a consistent reference frame, so I'm okay with that. Anything else? Why can I say that at the top of the swing for a split second? How? That's maximum height. So we end up with what would be a very complicated question to try and do with vectors and direction because of a constantly changing. It's doable with a constantly changing slope. Ugh. Scalar is very nice. A half little m v initial squared equals m g h final. Oh! Braden, what do you notice about this line here? I didn't grow up in Pitt Meadows. Is there a famous or good rope swing over Pitt Lake or something that people know about and go to? Kinda, yeah? Okay. I know growing up in Abbotsford, our local pool actually had a rope swing that we could use. Might not anymore because back in the 70s they were willing to be a lot more unsafe than they are now. Our playgrounds are better than your playgrounds, right? But yeah, it looks like... So what does the M canceling mean? I guess, Braden, it means as long as the rope doesn't break, if Tantor the elephant is running along at 8 meters per second, he'll swing to the same height as Tarzan. Yeah. What does it want us to get by itself? Okay. H is going to be V initial squared. I'm going to write it as over 2G instead of 1/2 because the 1 is kind of redundant in this situation here. It's going to be 8 squared divided by... By the way, Braden, if Tarzan runs twice as fast, will he go twice as high? 4 times as high, yeah. Because of that squared. Uh, 3.27 meters. Okay. Nicholas, you going to make it? Okay. Owen's blinking along too. I know I've been talking a while. Slap shots are great examples of energy transformations. Put your pencils down, look up. Looking at what I want to get through here, and I want to do more roller coasters. Okay. I'll pick this up a bit tomorrow. Let's finish with example 3. Your homework is the lesson from last day, which some of you got already. The roller coaster below has a mass of 255 kilograms. If the coaster just barely makes it over the first hill at A, how fast will it be going at B? Okay. It's a change in height, change in speed, definitely conservation of energy. So it's going to be initial kinetic, initial potential equals final kinetic, final potential. Sarah, are any of these 0? KEI, yep. I think one more is a 0. Are we ever on the ground? Yeah. So we get a complicated situation that again just ends up being mgh initial equals a half m v final squared. And oh, Sarah, have you gone on a roller coaster before? Before you got on, did they make you stand on a scale? No. Turns out the mass cancels. And again, we get an equation that we've seen a few times before. The final speed is going to be 2gh initial, square root of that. It's going to be the square root of 2 times 9.8 times 18. 18.8 times by 3.6. Not bad. I say it was? 18.8 meters per second. And then B says, suppose the roller coaster had an initial speed of 22 meters per second at A. How fast will it be going? Okay, again, it's going to be conservation of energy, G. Danica, which ones of these are 0? I don't think my initial kinetic this time. I think the only thing that's 0 is that one there. So I'm going to get a half m v initial squared plus m g h initial equals a half m v final squared. Danica, have you been on a roller coaster before? Before you got on, did they make you step on a scale? Here, I'm trying to get the VF by itself. Again, Paige, I'm going to clear fractions. I'm going to do that trick times by 2, times by 2, times by 2. Why did I do it here? Because there's 2 1/2s I can get rid of. If there's only 1 1/2, I usually don't. But if there's 2 of them, and also because it gives me a familiar equation, I end up with VI squared plus 2GHI equals VF squared. It's our old friend VF squared equals VI squared plus 2AD. How would I get rid of the squared? Okay, if we're coming over that first hill with some speed, 22 squared plus 2 times 9.8 times 18, square root of that. That's better. I get 28.9 meters per second. That's over 100, yeah. 60 miles an hour, 100 kilometers per hour. I'll go on that. We're going to pause here. We'll pick up with part C and finish this lesson off tomorrow.